Welcome to lecture number 9 in winter semester 2024, Introduction to the Lattice Boltzmann methods. So for last week there was no recording, but since this is an annual repeating lecture, you can go to the previous year and listen to the lecture from the previous time. This is also put into the playlist of this year's lecture. Okay, so today a continuation to the topic that was lecture 8, which is missing on YouTube, but you can listen to last year. We go on with multiple relaxation times methods. This time the real deal in 3 dimensions. We'll talk about moments, symmetries, and then the problems that we encounter, especially with the big ghosts. So the multiple relaxation time method for Lattice Boltzmann in Lattice Boltzmann is all related to this paper here, Multiple Relaxation Time Lattice Boltzmann Models in 3 Dimensions by DMYer from 2002. This is one of the best cited papers in the universe of Lattice Boltzmann, and it describes in particular unweighted orthogonal MRT methods for D3Q15 and D3Q19 lattices. So there are several things one could say about this paper. So the good thing, the important thing, is the historical significance of this idea. So it's a very important paper with new ideas. And on the downside, probably, is the correctness of this paper. I mean, not in the sense that there is a hell lot of typos or something like this, but the way the entire argument is built up with this orthogonalization, and in particular the relaxation rates that are used in this paper, even though they give concrete numbers. This is very questionable and actually no longer considered to be correct. So, but anyway, it was back then, it was a big deal, and it's still a very well cited paper. So what we are now going to do is to consider things that you don't read in the paper and probably also not in other papers. So what nobody told you about MRT is what you're going to learn here. Now, we use as one of our starting points, or as our starting point here, something a little bit different from what they used back then. We used the tensor product lattice. So tensor product lattice means we have a D3, 3 dimensions, Q tensor product 3 by the power of 3, which is D3Q27, for which there is no working Lattice Boltzmann model of the kind of the usual MRT methods. Actually, the way the usual MRT methods has been derived, quite interestingly, leads to an unstable method if you try to apply this to D3Q27. The reasons for this are a little bit complicated, but they can be derived. So, okay, what do we want to do? We started with the single relaxation time, BGK method, that has only one relaxation time. And now we discovered that the relaxation for the Navier-Stokes equation, to derive the Navier-Stokes equation, only some moments need to be relaxed with a certain rate and other moments may have different rates. And the question we are asking now is how many different rates can we actually use for any lattice. So, and the question is how many independent from each other relaxation rates or times, and this is the inverse, can be imposed under the assumption of isotropy. So in principle, you could say there are so and so many moments, and each of them has their own relaxation rate. Okay, right, but then your model wouldn't be isotropic. So for determining this isotropy, we use a grouping of moments. So we distinguish our moments in terms of what they actually mean, and we are now here using raw countable moments. These are not the moments that were used by Dehemier et al. Come to this later. So what moments do we have on our tensor product lattice? We have M000, M100, M010, and M001. They are conserved. So because they are conserved, there is no relaxation of them. So here there are no free parameters. Then we have this kind M110 with 3 permutations. Permutations means by exchanging the indices. Then we have M200 minus M02. So this is now a rearrangement. It is itself not a countable moment, because a countable moment is of course M200. So there are 2 countable moments, but we rearrange them in this way. And there we have this guy, and in order, because we rearrange them, we also have this what we call the trace. So these here are the hydrodynamic moments. And they have the relaxation rate, or inversely the relaxation time. Relaxation rate, we're now using the rate omega, which is the same as in the BGK. So they come with omega BGK. Now, and in this rearrangement where we have the M200 plus M020 plus M002, this here is the acoustic or energy mode moment. And we are going to relax this with omega p, which can be identified with the bulk viscosity. Okay, we'll not go into much detail about this. So now we have the conserved moments, we have the hydrodynamic moments, and we have the acoustic moment. And then we come to the ghost moments. So the ones that do not show up in the Navier-Stokes equation. And there are different groups of this. So we start, so this here were 0, first and second order moments, and now we are in third order moments, and we give a group third order moments A. This comes with M120, and this guy has 6 permutations. Then we have a group 3B. This is M111. This comes only with 1 permutation. These are the fourth order moments. Then the third order moments. Now we come to the fourth order moments. So group 4A is M220 times this comes with 3 permutations. And then there is a group B, M211. Again, there are 3 permutations. Then there is a group 5 of fifth order moments, M221. Again, this has 3 permutations. And then there is a single moment of sixth order, M222. Yeah, and these are all the moments that we have. Now, question. Has each of these types its own relaxation rate? Or could they even be more, actually? So, one thing that we observe from the acoustic moment and the hydrodynamic moments is that we have these guys here, which are one type, but actually they come with 2 different rates because we do a rearrangement in an isotropic and an anisotropic part. Yeah? So because this, take the isotropic part, which is this one, we take this out. Isotropy means it is invariant under rotation of the coordinate system. Invariant under rotation. So, isotropy is the thing we are concerned with, so we have to understand what it actually means to be invariant under rotation. And for this, we first have to see how moments actually rotate. So, talking about rotation of moments. Now, regarding our lattice velocity population, lattice velocity, the lattice velocity of a certain population. So we have the population Fijk, and we see this has a velocity xi, and this velocity is, of course, in terms of delta x by delta t. And here comes the vector I, j, and k, because I, j, and k are the directions in x, y, and z. So we can write this as I, the unit vector in x, plus j, the unit vector in y, plus k, the unit vector in z. And all of this multiplied by delta x and delta t, by delta t. So when instead of this we look at a rotated lattice in any by a rotation in any arbitrary direction, now we indicate the rotated vector by IR, JR, and KR. So R indicating that this is a rotated vector, and we can impose this rotation by multiplying the unit vectors with a rotation matrix. So this R is a rotation matrix, not specified how it looks. So J, the same rotation matrix, plus K, R, rotation matrix E, Z. So how does a rotation matrix look like? It can look different ways. I'm just giving here 3 specific rotations, which are relatively simple, namely the rotations about the axis, x, y, z axis. So if you are not familiar, just look it up in a math textbook or online. So rotation about the x-axis would look like this: 1, 0, 0, 0 cosine alpha. This is the angle of rotation, so how far do we rotate. Minus sine alpha, 0 sine alpha, and cosine alpha. So this would be a rotation about the x-axis. This is why we have here in the x 1, 1 direction we have here 1. Then rotation about the y-axis looks very similar, just by permutation. So we would have cosine alpha 0 sine alpha 0, 1, 0 minus sine alpha 0 cosine alpha, and also the rotation about the z-axis would look very similar. It's just cosine alpha minus sine alpha 0 sine alpha cosine alpha, again 0, 0, 0, 1. So these are 3 rotations specifically around an axis. So if now we rotate, we'll use the following nomenclature. If we rotate things about the x-axis, I will call this Ix, Jx, and Kx, and this would mean that I have I times Rx, Ex, plus J, Rx, E, Y, plus K, R, X, E, Z. So, as an example, we briefly consider why the acoustic moment actually is an isotropic moment. So we define the moment as MP. MP is the sum M200 plus M020. So this is the acoustic moment. And we can write this in terms of our population. We sum from minus ij in k from minus 1 to 1. And we have here I square plus j square plus k square fi j and k. So now what we just learned from the above is that we can write the rotated coordinate system. So we can rotate our coordinate system by replacing the I, the j, and the k with ix, jx, and kx. So that would give us things that are rotated around the x-axis. In particular, in the case here, if you put any rotation into this, and do the lengthy mass, what you would discover is that I rotated by anything square plus j rotated by anything square plus k rotated by anything square is the same as the thing before it was rotated. And this is what we mean by anisotropy. So in whatever orientation we take our coordinate system, we always get the same result for MP. We get always the same moment MP. And this is what we mean. It is invariant under rotation. Okay, so the actual computation of this could be a little bit lengthy, so you get a lot of sines and cosines, and you have to group them together to see that they all sum up to 1. So I'm not presenting the actual calculation here, but if you're interested, it's not extremely difficult, it's just lengthy. So instead of this, let's look at the hydrodynamic moments. Say we have the moment M20 minus M02 is equal to I, j, k from minus 1 to 1, I square minus j square. So we just track the definition, as we did in the previous example. We take the definition of these countable moments into the sum. And now this here we'll look at a specific rotation, namely the rotation about the z-axis. So how does this look like? Rotation about the z-axis, being more specific now here. So we have the vector of the rotated indices. This will be I times, now comes the rotated unit vector, and the rotated unit vector, if we do this, we come to cosine alpha, sine alpha, and 0. So you get this by having the rotation matrix that we have up here, yeah, and you're multiplying this with the vector 1, 0, 0, yeah, so you multiply by 1, 0, 0, you get cosine from in the first line you get cosine alpha, in the second line you get sine alpha, yeah. So, and similar j So you multiply, you multiply again this matrix with the vector 0, 1, 0. Yeah, so this gives you the second column in this matrix, and this is minus sine alpha, cosine alpha, and 0. And the last thing is you multiply the rotation matrix with 0, 0, 1, and then you get the last column, and the last column is just 0, 0, 1. So now this means, now for I z square, so I z square is what we need, that would be I cosine alpha minus j sine alpha square. Now let's do this. This is I square cosine square alpha minus 2ij cosine alpha sine alpha, and the second part here is plus j square sine alpha. Yes, and that's it. And we also have j z square. So this is I sine alpha plus j cosine alpha, and this gives us I square sine alpha square plus now 2ij cosine alpha sine alpha plus j square cosine alpha, cosine square alpha. So what we need in our equation up here is I square minus j square. So I z square minus j z square. And we are, of course, interested in grouping this according to I and j. So there's an I square that comes with the cosine square alpha minus sine square alpha. Then we have 4 times ij sine alpha, okay, I'm changing the direction, cosine alpha, and also we have j square sine alpha, sine square alpha minus cosine square alpha, which again we can, so this can actually be transformed. So you see they are similar. They have, this guy and this guy are similar. They have different sign, and also this can be transformed. So we'll take this out. So they have different sign. This is why I wrote I square minus j square, and they can be transformed to cosine 2 alpha, and the rest will be the same. For ij sine alpha cosine alpha. Okay, so what does this mean for the moment? This means that there is a potential change from I square minus j square. So this was what we had before, and you can see if we put 0 there, if you put 0 there, so no rotation, we'll get out what we got put in, and this will disappear. However, there's also the possibility that this here disappears and we'll have this guy here, and this guy here will come in ij. The moment over ij is obviously the moment m11. So this looks like this, ij k is minus 1 to 1, in ij, fij, k. So that means that the moment m200 minus m020 can be mapped on a different moment, so in a different coordinate system, the moment m200 minus m020 will become a moment m110 by rotation of alpha equals to pi quarter of pi. So sometimes this m200 minus m020 is called stretching, and m110 is called shearing. And what you should now observe is here for the if the isotropic part is taken out, then stretching and shearing is the same thing. It's just different by rotation about the coordinate axis. So, however, we also have to deal with the isotropy or anisotropic properties of our lattice, because the lattice maps in a different way. It only maps onto itself after rotation by n, where n is an integer, by n times pi half. So let's try to make kind of a picture. So say this is our lattice. So, and suppose we rotate the lattice. Let me do this in a different color. That's the wrong one. Now suppose we rotate the lattice by pi half, then, I mean, this point here will go here, this point here will go here, yeah? So basically, the lattice matches on itself for this kind of rotation. However, the rotation that we had just had been looking at, the rotation by quarter pi, if we rotate the entire thing by quarter pi, so only, not the entire way, but only until here, pi quarter. So what we'll observe is get something like so this will be our new lattice, and this here has, so to say, this has no match. This is not matching, and this here is matching. So if alpha is not equal to n pi half, there is a numerical difference So from a physical point of view, you should say they should match, but the discretization is not as isotropic as physics should be. Therefore, there is this mismatch. So this is a property of the lattice, it's not a property of the original equation. Let's look at the rotation of our ghost moments. Now we do this in order to identify in how many different relaxation rates we can put on the different ghost moments. So if there are moments that we can put onto each other by rotation, then they should probably have similar the same rates. And here, let us start with the group of the third order moments, and let us look specifically at a rearrangement of M to 1 minus M 0, 1, 2, which of course is obtained from this sum here, I square k square into j, and this into fijk. Okay, now let us rotate this guy specifically about these y-axis. So we have I y square minus ky square into j k, and this can be, I did this with Mathematica, so just give you the result now. If we do the rotation of the indices and simplify them, we get I square minus k square times j into cosine to alpha, similar to the above, minus 4i j k cosine alpha sine alpha. So this is basically pretty similar to what we had before with the other moment. So, and very similar to what we had before, we'll now observe that there is no rotation that maps M2 1 minus M02 onto M2 1 plus M012. And even though we did this in the context of our lattice, this is actually not depending on the lattice. So this would also be the case if we had the non-discretized momentum distribution. And therefore, this is actually a physical property of these moments, that they do not match on each other. So they genuinely represent different physical quantities. These things don't have anything to do with each other. And because they represent different physical things, they are also permitted to have different rates. They are not coupled by isotropy, so their different rates are admissible here. Whereas the moment M210 minus M012 by a rotation of pi quarter maps onto M111. So these two guys are physically in the same group, but anyway, because this is a rotation by pi quarter and rotating and the lattice by pi quarter does not map onto the new lattice, it means that they are numerically in different groups. So only due to the discrete distribution. But anyway, we put them into different groups. So this means for the third order moments, we have 3 different admissible relaxation rates or times. Okay, all right, rates. So we have the rate m for m2, 1, 0 plus m 0, 1, 2, and its 3 permutations. They are given the rate omega 3 plus. It's just a name. M210 minus, so this is physically different, and all its permutations are given the rate omega 3 minus. And then there is the moment M11, which we give the relaxation rate omega 111. So, again, what I wanted to say is that the relaxation of this M210 minus M012 when we do this differently from M111, then this would be anisotropic, or it is anisotropic, in an isotropic world or in an isotropic distribution. So I'm actually on record 18 years ago when I wrote my PhD thesis about these things. I said they have to relax with the same rates because they can be mapped onto each other. So in the meantime, I think I understand these things better, and what we sometimes find is if the lattice already is anisotropic, first of all, you don't gain anything by trying to make the distribution then more isotropic. On the contrary, you could actually gain something by doing the opposite, namely, when the lattice itself has this level of anisotropy, then it's sometimes possible, and actually in this place it is possible, that 2 anisotropies cancel each other out. So what we actually do in practice is that we deliberately take omega 111 different from omega 3 minus in order to cancel out some anisotropies in the lattice. Yeah? So this is what is in practice done. but we don't go into that detail here today. Okay, let's look at our forced moments. So again, here we have something that looks isotropic, M220, M202 plus M022, which would be computed from Mijk from -1 to 1 into I square j square plus I square k square plus j square k square, and this into this population Fijk. So what we find if we put all of this in Mathematica or do it by hand, which is quite some work, that this for arbitrary real rotations maps onto itself. So I are any rotation of this plus I r k r both square plus j r square k r square is always I square j square plus I square k square plus j square k square, and so this moment here is isotropic. So if this moment is isotropic, then there will be others that are not isotropic. So we'll take others out, like M220 minus M202, and we'll rotate this about the x-axis. X-axis. So we get ix squared j x squared minus k kx square is equal to I square j square k square. So this is again looking similar to what we had, cosine alpha. Here's a bit difference, 2I square, sorry, 2I square jk and sine 2 alpha. So again, what we observe, that M220 minus M202 maps by a rotation of alpha equal to pi quarter, which again is not the right value for the lattice, will map into this moment. So physically they should behave the same, but since the lattice has the anisotropy by a rotation of pi quarter, we put them into different categories, and so we have here three different moments, namely the moment M220 plus M202 plus M022. It gets the rate omega 4 plus. Then we have M220 minus M202. This comes into three permutations. And has the rate omega 4 minus. And then there's M211, which comes in three permutations. And is given the rate M omega 211. So, and in addition to this, we have we could call them the higher ghosts, so the ghosts of fifth and sixth order. So they are relatively sparse, so there's only the one M221, yeah, that comes in three permutations. So there's only one rate here. And for the sixth order moment, there's only one, so there can only be one relaxation rate. Okay, so these are all our relaxation rates, and if I didn't make a mistake, they sum up to 10. So we'll have 10 different relaxation rates in this model. Okay, now we have identified how many different rates we have. Then we come to the next chapter in the development of the MRT method, that is the orthogonality. Of moments. And this is the topic, I would say, that saw the most change in opinion and understanding in the last 10 years. And this is in particular the point what the original MRT method, actually what we call the classical MRT method, got terribly wrong. So the classical MRT uses an orthogonalization that we now call, they didn't call it that way, but now we call this unweighted orthogonality. So unweighted orthogonality means the following. I've already introduced this. So we're talking about a moment, say m phi, that is defined by a kernel function, ijk from, okay, so there doesn't need to be, so it could be for different lattices. This is why I don't write bounds here. So there is a kernel phi ijk into fijk, and this gives us the moment phi, okay? So for example, countable moments would here have I by the power of A, J by the power of B, K by the power of C, yeah? So, and now there is a different moment, MC over I, J, and K, with Psi, J, K. So now these are different kernels for different moments. Yeah. So the question is, when are these moments orthogonal to each other? And in the classical MRT, we define them as unweighted orthogonal if they have the property that the sum over ijk, psi ijk into psi ijk, if this gives 0, then we call these things orthogonal. Now, problem is, it turns out that whether you make things orthogonal or not has extremely little effect in 2 dimensions. And the way everything here developed is kind of, oh, you do it first in 2 dimensions, then you are happy with your result, and then you say extension to 3 dimensions is straightforward. Yeah, I read this sentence very often in papers 20 years old or so, and it turned out that the generalization to 3 dimensions is absolutely not straightforward, and this should actually be known from the Navier-Stokes equation itself, because the Navier-Stokes equation itself in 2 dimensions and in 3 dimensions behaves completely differently. Yeah? So there is, for example, in 3 dimensions we have turbulence. In 2 dimensions it's not even, some people talk about 2-dimensional turbulence, but 2-dimensional turbulence is not the same thing as three-dimensional turbulence just in 2 dimensions. Yeah, is something completely different. So what turns out, using orthogonalization, using no orthogonalization, whatever, in 2D, we'll see no difference. Yeah? And actually, you can also prove why this is the case, but let's skip this here and just say when you use this kind of orthogonalization, you produce big problems in 3D. So by big problems in 3D, I mean you're really killing it. So the orthogonalization makes things worse. And one of the things that nobody told you about, that the papers don't tell you about MRT, is when you try to make a classical MRT method with a D3Q27 lattice. Yeah, that was never done, apparently. If you do it this way and you use the usual orthogonalization, then your method is completely unstable and unusable. So what back then they said, okay, we are using D3Q19, we never tried D3Q27. I actually don't believe they never tried. They never succeeded. Yeah, and they didn't know why they didn't succeed. But the reason is that orthogonalizing a D3Q27 lattice in this way makes your method unstable. This is why it couldn't work. Okay, we are now looking at these examples because when I was younger, I actually tried this out and made a model, usual MRT model with D3Q27, and I also designed a specific test because I already know from my analytical not analytical, I mean theoretical considerations, what will go wrong. So I designed an experiment particular, so this looks a little bit strange, it's a double shear wave experiment. This is designed such as to show the problem that occurs here. So this is a problem with an analytical, where the Navier-Stokes equation has an analytical solution because it's in a very simple flow. And we have an analytical solution in a periodic box, and this box has a size, let's call it L times delta x. Delta x means there's only one grid spacing in the x direction times, so these are times, and the other one is an x. I should make it smaller and the x bigger. It's probably better. And 3/2 L. Okay. So the thing looks like this. So there's an ux is completely 0. Then there's a uy that's given as u0 else 0 by L sine 2 pi x divided by L cosine 4 pi divided by 3L, and this into Z, and all of this decays with the viscosity over time, and 2 pi divided by L squared plus 4/3 2 pi L squared. Okay, so this is how this decays, and the velocity in Z direction is also 0. There's a very unnatural flow, but it is a flow that highlights a very simple flow, and it highlights what the problem is. So now what you're doing with this is you init the simulation with a given velocity u0, then you run it, then you measure the decay, so because this decays with this exponential function, measure decay, then you fit the measured decay, with the measured decay you fit a viscosity that you call numeric, new numeric, and then you compute the error. Then you compute the error. So, and the error we define as the viscosity that we impose, the viscosity minus the viscosity that we get out of the fit, and we divide this by the viscosity that we impose, and we'll also take the absolute value of this. And now we do this for different resolutions in diffusive scaling. And what we are using is we put all the hydrodynamic moments, omega, we put omega as to omega bgk, and all the ghosts, moments, omega ghost, all the others, we put them to 1. And of course, now this is the moment when the advocates of the MRT method would then usually say, oh, you're doing everything wrong. I mean, the thing with this relaxation rate is, so what they always claimed, and everybody who was not in the MRT camp was just getting annoyed with this, is, you know, if you get a bad result with the MRT method, then you simply used the wrong relaxation rates, right? And problem is, you can always say this, and nobody told there was no way to determine what is the right relaxation rate. So you could always say you are doing something wrong, yeah? So there is an infinite space of different relaxation rates, and if you had put the right relaxation rate, you get the right result, yeah? So problem of MRT method is it's a model with 9 arbitrary parameters that you can choose anyway, and now you're on your own. Yeah, do what you want, and if you put them correctly, then you should get a nice result. So, if in the absence of any better knowledge, we put them to 1. So what happens if we put them to 1? Let's see. So we have here some results actually. Don't know why it's doing it this way. Okay, so this is these are different methods that were used here, and what we did is so for different viscosities and for different resolutions, and what we observe is, okay, we get usually second order accuracy with this. Now there's a cumulant method in this. This is something that we learn later. There's a BGK method. There's a cascaded method. We are not talking about this. What we want to look at in particular, because this is the ones that we have already mentioned, is we have the BGK, this is the blue one. So the blue one usually it's quite astonishing. Yeah, so you spend a lot of work in building these movements. There's other models, but the blue one is pretty good. So the error is the smallest. And here we have in this magenta thing, we have the MRT method, the usual MRT method, or the MRT method with the D3Q27 lattice, which is made orthogonal. And if you look at these pictures at viscosity 10 by the power of minus 4, 3 by the power of minus 4, minus 5, you don't see these MRT results because the method was unstable everywhere. It's only stable at very high viscosity. Yeah? So at a very high viscosity, it is here where also the error is relatively large. So because the line, so error is here, so if the line is up, the error is large. And in all other cases, it's unstable. What we call here rare moments, so this is the green one. Yeah, so the green one is also sometimes unstable. You probably don't see it because it's below the red here, so it's unstable in many cases, but it has a stable range. And here it's behind the red one, so we actually have it here. Here we have one dot where it's actually stable, so it's not stable everywhere. But the rare moment method, even though it has a similar error, so rare moment just means non-orthogonal MRT, yeah, without orthogonalization. Similar error, but more stable. So let's just write this down. The observation is orthogonal MRT is unstable. Rare moment MRT has large error. So both is not very good for a paper that gets so many citations. This orthogonalization leads to instability, and we'll spend the rest of the lecture to try to understand why this is the case. So for this, we go back, of course, as always, to our asymptotic analysis. So this again was in lecture 6, and we'll put it to second order. So we'll have the moment MABC with an overbar to second order. Yeah, can be written down as MABC equilibrium to second order minus, here comes the relaxation rate associated with this particular moment, and this goes into dx A plus 1 BC first order plus dy MA B plus 1C first order. Now this is different from lecture 6 by actually having them in 3 dimensions now, dy A B C plus 1 first order, and now closing the brackets. Now this can be evaluated specifically for A is equal to 2, B is equal to 1, and C is equal to 1. So this is something that we didn't do in lecture 6 because this is looking at the ghost moments. Yeah? So because our problem is obviously with the ghost moments, yeah, because this is where the difference is, and this is where different orthogonalizations make a change. So ghost moment is a first order moment. Let's look at this first order moment. How does it look like? It's M211 to second order is M211 to second order equilibrium minus 1 over omega M211, if this is the rate, then dx M311. So you already see that this here is actually an alien. dy M221 to first order, and dz M212 to to first order. Okay, so now we have to put in these things which we don't know. For example, the equilibrium, so the equilibrium M2 to equilibrium 2. Now this can be written down through factorization. That's much easier than taking the original integral. So it will be the zero order of M2, 0, 0, the first order of this and the zero order of this, and there will be no other permutation of this because, you know, a second moment has only odd, has only even parts, and an even moment has even, the first order moment has even only odd parts. So this is why this will disappear, and this, all of this divided by M0, so it is normalized by the density square, which gives you theta uy 1 uz 1 and rho to the zero order. So this is what the equilibrium for this first order moment looks like. Now let us call this next equation 9.1. We say that M211, so this is again the equation above, written in this way. Okay, before I do this, sorry, I kind of missed one thing. I did not specify, the other guys. The other guys is M311 bar. So this is an alien, so this is the same thing as M11 over bar 1. And the first order of this is 0. So to first order, third order moments, and fifth order moments are the same as their equilibrium, so can write this here. This here is, you get this again through factorization, and this would give you theta square rho 0 and uy first order, and similarly M2 to 1 to first order is giving you theta square rho 0 u z to first order. Okay, so now with this in place, we can rewrite the equation again, where we replace the equilibrium u z first order minus, now relaxation rate, omega 2 to minus 1/2. Okay, so then in front of the others, there is theta rho 0, theta square rho 0. Then comes the derivatives, dy u z first order plus d z u y first order. The derivative in x will disappear because the respective moment here is 0 to first order, so it is gone. Okay, now this is the equation that comes out for this first order moment. Now the interesting thing is, this is a first order moment that is specific to the three-dimensional case, because all the three indices are different from 0. So we cannot investigate this case in a two-dimensional problem. So if this makes any trouble, then this trouble will not show up in a two-dimensional simulation, and it doesn't. Yeah? So this is why in 2D everything is fine. Now here in 3D there's something different going on. And the thing that is going on is seen by looking at this here. Because this here, so these derivatives here, is something that we've already seen in a hydrodynamic moment. specifically if we put A equal to 0, B equal to 1, and C equal to 1. So then we have the hydrodynamic moment M011. So this is a guy that also exists in 2 dimensions. This is rho 0, so the equilibrium. Uy to the first order, uz to the first order, that's the equilibrium. Here comes, because the hydrodynamic moment, it comes with the BGK relaxation rate, minus 1/2. It comes with theta, rho 0, and here there is the same term as the above. Okay, so this reappears. Okay, it reappears. So what? It reappears. So what this means, that the moment M211 and M011, they must be coupled. Yeah, because they completely depend on the same thing. However, the entire idea behind the MRT approach with the different relaxation rates is that these things are not coupled. I mean, in order to have these gradient terms here decay at different rates, they must be different. If they are the same, then obviously they cannot decay with different rates. This doesn't make sense, and it actually doesn't work. Let's look at this equation in a little bit more detail now. So say we take this part here out and say this is theta rho 0 dy uz first order plus dz uy first order. Now we put everything else on the other side and we'll get to a minus m. So this hydrodynamic moment minus its equilibrium, uy first order, uz first order, and now we divide this by the relaxation. Yeah, so, and now we see the gradient, this gradient term, yeah, which depends on the solution of the Navier-Stokes equation, because here's u1. So you take the solution of the Navier-Stokes equation, then this moment, the moment M01 has to satisfy this condition. And this is something that also appears in the equation 9.1. Okay, let's put it into equation 9.1. What happens? So we then have the moment M211 to second order. Here comes the equilibrium rho, theta rho 0, uy first order, uz first order. And now we put all of this into the place, into this place. Yeah, so we'll still have this here in front, and we'll have this guy here. So we'll have 1 minus 1 minus 1/2 divided by 1 over omega bgk minus 1/2, and this goes into theta m I may be, where am I? Okay, I may have made a mistake here with my signs. Minus rho 0 uy first order uz first order. Well, yeah. And now this is how it looks like. So now we can make a relationship between the moment M211, which again, as I said, is a moment that doesn't exist in 2 dimensions, so it doesn't matter in 2 dimensions, obviously. And also, it does not exist as an independent variable on the D3Q19 lattice. Yeah? This is also the case. Now, in D3Q27 it exists, and there's a relationship between this moment and that moment directly, and so it does not depend anymore on any gradients here. So all the gradients are now eliminated from this equation. Okay, and the important thing we want to look at is this ratio between the different relaxation rates. So first of all, pretty trivially, in BGK, all the relaxation rates, this is the essence of BGK, all the relaxation rates are the same. So these are the same. So would mean that we have 1 over omega 2, 1, 1 minus 1 half divided by 1 over omega BGK minus 1 half is equal to 1. Okay? So, great. Then this would simply mean that there is a proportionality between one moment and the other. Yeah? So no big deal. What is with MRT? So in MRT, what we want to do usually is we want to simulate high Reynolds number flow. High Reynolds number flow means low viscosity. Low viscosity means omega BGK is going close to 2. Then the original idea of having more relaxation rates is to put some damping on the higher order moments. So the higher order moments, the ghost moments, yeah? And this can be done by, for example, putting them to 1. Yeah? So this is damping these moments. So what does it mean? It means that 1 over omega 2, 1, 1 minus 1 half, 1 over omega BGK minus 1 half, so this guy goes to infinity. Now, yeah, because the viscosity, this here, down here is the viscosity is getting small, the damping of the ghost moments is large, so this is going to be large. Okay? So this is the problem, because they are, this M211, we usually say this doesn't matter because it's a ghost. However, we multiply it with something that goes to infinity, so it's a ghost. It does not appear in the Navier-Stokes equation at leading order, but it is a very big ghost because it's proportional to an existing moment and to a hydrodynamic moment, and it's much, much larger than that one. So it's a big ghost, and therefore it of course makes a difference and may cause the system to be unstable. But now wait a minute. I was bashing the original MRT, yeah? And the original MRT uses orthogonal moments, and this here is a non-orthogonalized moment. It's using directly the raw moments without orthogonalization. So let's look what happens if we use the orthogonalization. That is from the classical MRT, so this is the unweighted orthogonality. Unweighted orthogonal MRT moments. So, and now we have to redefine them. So we'll call this moment now N211, and this orthogonality, by making them orthogonal, what comes out unweighted orthogonal, it's 3 times 3m211 minus 2m01, so these are unweighted orthogonal moments on this D3Q27 lattice. So we see there's a combination of the two moments we have just been talking about, and if this combination is a clever combination, actually they may cancel each other out. Let's see whether this is a clever combination as it was supposed to be. So we look at the asymptotic expansion of this, again to second order. Here we have to put in the expansion of the moment M211 and the expansion of the moment M011. This look like this. So we have the equilibrium distribution first. So it's the equilibrium to second order minus 2 times M011 equilibrium to second order. Now we relax this with our ghost rate M1 over omega g minus 1/2. There's a rho 0. And if we put everything into it, and hopefully I've done this correctly, then we get here 3 theta square minus 2 theta, and all of this goes into dy u z first order plus d z u y first order. And what we see is they are not disappearing. These guys are not disappearing. Now we can again substitute this here, which was not disappearing, with the solution of the M011. And this will give us 3m211 equilibrium that I don't write out, so this is just a function of the velocities, minus 2011 equilibrium to second order. So we get something extremely similar here again. Yeah, 1 over omega g minus 1/2, 1 over omega bgk minus 1/2, and this goes into 3 theta minus 2, and this is M011 to second order minus rho 0 u y. So this is the equilibrium of the guy. Okay, so this is just taking out the equilibrium. So the same thing, the only thing that changed here is the only thing that changed here is the sign. By the way, I'm just recognizing that something with the sign, I must have done something wrong with the signs. I must have done something wrong with the signs. There must be, so I take, because there's this sign, I must take this one down here, and this must be this one. Okay, sorry for having the wrong sign. Right, so what does it mean? It actually means it didn't work. Still large, only different sign. Actually, this could mean it's even worse. But from an absolute, the absolute value of the error actually didn't change. It's just the error in the other direction. And as we observed with our simulation, this was even less stable, so it's probably even worse. So, question, the last one for today. Is there a better way to do it? And of course, when we talk about unweighted orthogonality, and they didn't call it unweighted orthogonality, we call it unweighted orthogonality, then you can guess that there's a solution that is the weighted orthogonality. Now the problem that we had here is that by making it orthogonal, the dependency didn't disappear. Yeah? Let's see whether we are able to make the dependency disappear and introduce a new weighted orthogonal moment that we call n, now small n, 2, 1, 1, and we define this as m 2, 1, 1. So this should have the information from this, and we want this to be independent of m0, 1, 1. Now we remember that we can actually factorize this moment and say that that should be kind of proportional to m200 times m11, and this probably normalized by something. Yeah. So if this looks like this, then you remember that m200 should be proportional to actually theta. So one idea you could have is multiplying this by theta m00. Yeah? If you multiply this by theta, take m011, yeah, and try it with this. Let's see what happens if we try it with this instead. Now this is a different way of orthogonalizing it. So again, to second order, putting in the equations. Minus theta m011. So here comes the equilibria, second order. It comes minus 1 over omega g minus 1/2. So we relax this moment here. We get theta square rho 0, and indeed we get theta square minus theta square rho 0. So this is what we multiply to dy u z first order plus d z u y first order. And now you see this here is 0. So there is no dependency here on this gradient term, and therefore this will just disappear. So there will be no dependency. We have no dependency. Okay. No dependency means that this moment m211 does not grow together with the moment m with the I mean it does not grow with the m011 independent of the relaxation rate. But now wait a minute. This again is a different moment, and it's not the same moment we have been looking on before. Now, therefore, let us briefly look into the original countable moment, m211 to second order, assuming, so we look at this moment, but the moment that we are relaxing, where we put the collision operator on, is the moment m211. So and now we express the moment m211 by the moment n1 m211 to second order. So this is, we have to inverse this operation. Yeah. So previously we subtracted theta. Now theta m011. Now we add this again. So we recompute this, and now we plug in everything again, m11 equilibrium. So this is what's coming out, plus theta 1 over omega bg k minus 1/2, and you get theta rho 0. Now, you see, this moment is not independent of M011. However, if you look at it, now previously we divided by viscosity, now we multiply by viscosity. Dividing by viscosity makes this moment very large. It was the same moment. It would be very large in the orthogonales, in the unweighted orthogonal way. But if we put it in the weighted orthogonal way, it's multiplied by viscosity, and therefore this is now very small. And this is now a good ghost because it is small, and so it is unlikely to make any trouble. And this is one of the most exciting findings, I would say, during the last 15 years in the Lattice-Boltzmann methods. Okay, thank you for attending. See you next year.